Alright, hi everybody. Today we're going to be working on the Chapter 4 practice problems. For this particular set, we're going to focus on some of the more basic concepts in sections 1 through 3. First, we're going to start with our dissolved species. So here, if you do not recall, Cn is a polyatomic ion referred to as cyanide. K is going to be a metal with a +1 charge. Cn is going to be a metal with a non-metallic polyatomic ion that's going to have a charge of -1. So when we say this thing is going to dissolve, remember that means dissociate or break apart into its ions. So we have to be able to figure out what ions is going to break apart. In this particular case, you would just have to have remembered that KCN, K is the metal and the Cn is the non-metal. In this one, we're going to do the same thing, so it's the same idea. What dissolved species are present? Again, you should recognize a polyatomic ion. When these two things dissociate, we're going to dissociate into a sodium metal, which is a +1 charge, based on its location and based on the charge of the polyatomic ion that it's attached to. Okay, from here we want to reference our solubility rules. Okay, so for this I would ask that you pull up the solubility table that has the solubles, the insolubles, and then the exceptions. So these are the rules. Remember, we talked about this in our last video. I'd ask that you have this up in front of you while you're trying to answer the questions like this. In this particular case, the first one I see is the sodium nitrate. Remember that we're always going to look at the identity of the anion first. Could be a polyatomic anion as well. Either way, it needs to be an anion to look at first. So in this case, we have NO3, which is a nitrate. All nitrates are soluble according to our table. No exceptions. So this one is going to be soluble. Okay. So we're going to write AQ underneath it or next to it to indicate that it is in fact soluble. All right, next up I've got sulfide. I've got calcium sulfide. I want to look up the anion S2- according to the periodic table and where it's located. That is the one that we should be looking up, is the sulfur, and it should be a 2- charge. It looks like all sulfides are insoluble, so this is where these sulfides are going to be located on our chart. And then it says one of the exceptions is compounds that include the metal cations calcium, strontium, barium, and of course ammonium. So this guy is one of the exceptions to the insolubility, which makes it soluble. AKA, when we write it in solution, it should have an AQ after it. All right, next up is going to be our magnesium phosphate. So again, I'm looking at the phosphate ion. The phosphate ion, PO43-. It says that all of these are insoluble, with the exception of the different, I think it says alkali metals. According to this, it says alkali metals. Is that right? And alkali metals are going to be the group 1 metals, which are like lithium, sodium, potassium, rubidium. Magnesium is not part of that, so this is going to be insoluble, which means when in solution it would form a solid. All right, next one's going to be our chlorides. We're going to look at the chlorides. On our table, it is in the list of all soluble. And strontium is not listed as one of the exceptions, so this is going to be an aqueous soluble compound. Okay, really you just need practice reading the table. That's what we're doing here. And then after this, we take it into account when we're doing our net ionic equations. And so for our last one, we got sulfates. According to our table, all things of sulfate are soluble, with the exception of strontium, barium, mercury, 2 plus, and lead, 2 plus. And since none of these fall under this category, aka ammonia is not listed, this is going to be a soluble compound. So we would label it as aqueous if we had it on a solution, okay? All right, let's do another one. Write the balanced chemical equation for the following reaction. So here's where we're going to take what we know about the solubility things and what we know about double exchange reactions, and we're going to write or predict what's going to happen on the right side of our equation. So in order to do this, first thing we're going to do is we're going to break these things apart. I need to know what the charges are of these things before I try to write stuff on the right side of my equation, because the charges should not change from left to right. Now, of course, this is double displacement reactions and double displacement reactions only. In future reactions, like oxidation reduction reactions, charges will change from left to right. But for now, charges should stay the same. Okay? Same on both sides. So that means over here I've got Na and I've got CO3 2 minus. Of course, there's 2 Na on this side, and there's 1 CO3 2 minus. Over here I've got 1 silver ion, which is going to be a +1 charge. The reason I know it's +1 is because there's only 1 nitrate, which is always a -1. So these two you should have memorized because there are some of our polyatomic ions we talked about memorizing. And then the other two are going to be ones that you can either guess from there or, like in the case of sodium, are going to be one of those common charges from the periodic table. So what we're going to do next is we're going to switch them. So sodium is going to gather with nitrate and silver is going to gather with carbonate. Remember that when we switch, the charges stay the same, and we're going to do that cross method. So since this is a 2 minus, we're going to take that 2 and we're going to cross it down. We're going to take that 1, we're going to cross it down here, and we're going to get Ag 2, sorry, CO3, and we're going to leave the state because we're going to double check what the solubilities are here in a second, and then we're going to get NaNO3 because there's a +1. Sorry, let me go back up here. So then we're going to do Na +1 and NO3 -1. We're going to take the ones, we're going to crisscross, and we're going to get that it's just NaNO3, okay? Now, we have to do a couple things. First is balance the equation, all right? So I'm just going to erase some stuff to make it look a little bit prettier. You know the crisscross method. I've got 2 sodium on this side. I need 2 on this side. Did I balance that wrong? No, I did. Okay. Then I'm going to put a 2 on this side to balance it, right? And then everything else should have a 1. Okay. Next up, let me just erase this as well. Next up is going to be to determine the solubility states of both the carbonate and the nitrate compound. So again, we're going to go over to our solubility table, and I'm going to look up and see that the nitrates are always soluble. It's like one that like I told you in our video before, you're going to start to recognize that nitrates are always soluble no matter what. There is no exception to that rule. So that's always going to be an aqueous compound. And then for our carbonate compound, I have that all carbonates are insoluble with the exception of NH4 ions, so ammonium, and alkali metal cations, also known as the group 1 metals. Silver is a transition metal and is not in that exception, so silver carbonate is going to be my solid in this particular case. Now, we didn't necessarily know that this was going to be a precipitation reaction, but based on what we've talked about in the last couple of days, you should be able to recognize that if I'm asking you to write me the products of a reaction, it probably means it's a precipitation reaction, 1, and 2, you're going to have to use the solubility rules to figure it out. So this is the answer to the question, is to finish off this reaction, we had to write the right side equation, and we had to balance, and we had to figure out our states. All right, next one. All right, we're going to do the same process. So first thing I'm going to do is I'm going to break them down, and I'm going to try to determine what our charges are. Now here, I have 2 nitrates, Each one is -1, which means that the total charge, whoopsies, so sorry. Which means the total charge is going to be a -2. And then that makes the lead a +2 as a result. So I'm going to get Pb2+ as the other species in this particular compound. Over here, I'm going to do the same thing. I've got SO4. I know that that should be a 2- because I've memorized my periodic table. I'm sorry, my polyatomic ion charges. And with my iron, because that one is a 2-, this iron must be a 2+. All right, so next thing we're going to do is we're going to try to predict what happens. We're going to switch the anion and cations around, and we're going to rewrite what we get. First thing I'm going to write, and I'm going to try to write it down here because it'll look a little less sloppy, is I'm going to write out how I'm going to crisscross. So I'm going to do 2s. And remember that when you rewrite them, that 2s, if they're both 2s, they simplify, and it just becomes the 1s, right? You can simplify. All right, next thing we're going to do, and we're going to leave, remember, we're going to leave the state alone because we're going to come back to that at the end. Next thing we're going to do is we're going to predict the other compound, which is going to be Fe2+ and NO3 -1. Remember, we're going to take the charge, crissy-crossy, and we're going to get Fe NO3 2. Okay? All right, so that's how we get our actual species. Next thing we need to do is we need to go to our insolubility table, or our solubility table, if you will. We need to figure out which one is solid and which one is liquid. Remembering, again, nitrates are always aqueous, regardless of what they are attached to. And our sulfate compound, in this case, I would predict that it's going to be insoluble, just because the other thing is soluble. But since we don't know if it's a precipitation reaction or not, we do actually have to look it up. So on our table, it says all sulfates are soluble. They're in the top part of that table. They're up here. And then these are the exceptions to the rule. We'll call them exceptions. So the soluble compound is going to be up here. This is where my sulfates are listed. Because of that, I know that the sulfate is going to be soluble unless it is attached to lead 2+. Look at that. So this is going to end up being our solid. Now, if you know you have a precipitation reaction and you know that one of them is aqueous on the right side, the other one by default has to be solid. So if you can identify the aqueous substance, then you know the other thing has to be solid. Just make sure that you know you're dealing with a double displacement precipitation reaction before you make that assumption. All right, let's do another one. I've got NH4 +1, which I remember. I've got PO4 3-, again, another one I should have memorized. I've got chlorine. Chlorine should have a -1 because it's a group 17 halogen, and then calcium, because there are 2 chlorines, is a 2+, also because of where it's located. So I'm going to play some switching around. I'm going to put the calcium with the phosphate. I'm going to put the ammonium with the chloride, and then I'm going to write out what I get. Since these are both 1-to-1, my compound's going to be NH4Cl. And since these are, what is it, PO4 3- and calcium 2+, we're going to take the 2, take the 3, and we're going to cross, and we're going to get Ca3, PO4 2. Okay. One thing we need to do at this point is we need to balance. I don't believe that I balanced the last one, but I think it was just like 1-to-1 switching. If not, go back and balance it for me. So here I've got 3 calcium, so I'm going to put a 3 here. And I've got 2 phosphates, so I'm going to put a 2 here. Looks like I'm going to put a 6 in front of here, and that should balance the equation. All right, next thing is to figure out what's soluble and what is insoluble. And here, I don't see anything that's obvious aqueous. I would have to go to my solubility table for a problem like this. So because chlorides are all insoluble, with the exceptions of silver, mercury, and lead, and I don't have that memorized, I know that this one is the aqueous compound. It said all of them are soluble. I meant to say soluble. If I said insoluble, I apologize. It says all chlorides are soluble with the exception of silver, mercury, and lead, and none of those apply to this situation. So by default, this one is probably going to be our solid, but always double check. It says phosphates are all insoluble with the exception of NH4 and group 1 metals, alkali metals, which calcium is a group 2 metal, so this one must be the solid in this particular case. Hopefully you're starting to get the hang of this one. There are a couple on your homework set that you need to do on your own. But if you have questions, this is a concept to definitely ask me, because the next thing we're going to do is we're going to be working on the ionic equations of these here in the near future. Let me double check. I didn't. Oh, nope. See, this one, we're supposed to take it one step further and write a net ionic equation. So I'm going to go ahead and I am going to use what I had before. Actually, no, I'm not, because now that I've balanced it, I'm going to have more of those ions. And remember that these coefficients matter when you're breaking them down into their individual ions. All right, so let's go ahead and let's do this one. Net ionic equation is the next step. So first thing I'm going to do is I'm going to break everything apart. Here I have 2 times 3 is 6 of the NH4 ion. I know it's a +1. I have 2 of the phosphate ion. Then I'm going to move on to calcium chloride. I've got 3 calcium 2+ ions, and I've got 6 chlorine ions. And the reason I have 6 of them is I've got a 2 times 3, that makes 6. All right, on the right side, I'm going to break this one down, but I'm not going to break this one down. So I'm just going to rewrite the calcium phosphate, because I know I can't break it apart. Everything else is breaking apart. And then I'm going to break apart my 6 ammonium and 6 chlorines. All right, so now that I've broken it down, next thing I'm going to do is cross off what cancels on both sides. I see a chlorine and a chlorine. I see an ammonium and an ammonium. Everything else should stick around because, of course, calcium plus phosphate makes calcium phosphate. So then I'm just going to rewrite. I like to put my metal first just because that's how I was trained. It does not matter. If you leave it the way it is, you're going to get the points either way. I just like the way it looks. And there's our net ionic equation. So 2 questions we were asked: write the balanced chemical equation and the net ionic equation. All right, I am going to pause here and I'm going to split this into 2 parts. So be right back.